Okay, this is ELEC1 2019 question 4. Okay, so for part A, the graph shows the frequency response of a voltage amplifier. Use the graph to estimate its bandwidth. Okay, so here's our graph. Voltage gain against frequency. Now to find bandwidth, you need 50% power. 50% power is 70% voltage or voltage gain. So to find the bandwidth, we need 70% of the voltage gain, so 0.7 times maximum voltage gain, which is 50. It's going to be 35. So 35 is a key value as far as this graph is concerned. Okay, so let me just make sure I've got it. Right, so 35. Okay, we're going to use a graph to draw the bandwidth. Let's get this in the right place. So at 35, we're going to draw a line across to where we meet the graph. And then we're going to draw a vertical line to find the bandwidth. And where this intercepts the y-axis, sorry, the x-axis is 5,000. So our bandwidth is 5,000 hertz, which is 5 kilohertz. Okay, part B. Part B is all about this circuit diagram. The circuit diagram shows a voltage amplifier using an op-amp with a slew rate of 4 volts per microsecond. Now that value is going to be important later. Its output has saturation voltages of plus 12 volts and minus 12 volts. And then we've got our circuit diagram. And we need to recognize that this is an inverting negative feedback amplifier. And that's going to be important as far as the equation is concerned and part 1. Because part 1 says state the input impedance of an amplifier. Now for an inverting negative feedback amplifier, the input impedance is equal to Rin. And in this particular example, Rin is 12 kilo ohms. Then part 2, what is the maximum input voltage that avoids clipping? Okay, so we need to understand what clipping is, and clipping is where the output has saturated. And that's where these saturation values of plus 12 volts and minus 12 volts are important. So we need to calculate V in. So if we rearrange the inverting negative feedback amplifier equation, then V in is equal to V out over gain. Now we don't have the gain, but we do have the values from the graph. Now the gain equation for a negative feedback inverting amplifier is minus RF over Rin. So it's going to be minus 360 over 12, which is minus 30. Now we can find out V in, because V in is going to be plus or minus 12, those saturated outputs, divided by minus 30. And that will give us values of plus or minus 0.4 volts. Okay, part 3. Signal shown in the first graph is applied to the input of the amplifier. Use the axis to draw the resulting output signal. Now for this type of question, you need to ascertain 3 things before you can actually go on to draw the output graph. And those 3 things are, does it invert or not? What are the values of the output going to be? And how long does it take to go from the lowest value to the maximum value for your output graph? Now the first one is we know it inverts. So we know that our negative V in value, which goes from 0 to minus 10, is going to be inverted. It's going to be positive, so we know it's going to invert, and that's quite important to get that right. The second is, what are the maximum values of V out going to be? Now, if you look at the V in value, the maximum value, it's minus 10. And that's a large value, and for this type of question they normally give you large V-in values because what they want you to do is to realize that the output saturates. Therefore, we know that the output, the out, is going to go from 0 to 12 volts, and that's plus 12 volts because it's inverting. And lastly, we need to work out how long it takes to actually change. Now we know that the slew rate is 4 volts per microsecond, and what this means is for every microsecond the output increases by 4 volts. Now it's got to increase from 0 to 12. That's therefore going to take 3 microseconds. So time is going to be 3 microseconds for the change. Right, now we have all the information that we require in order to draw V out. Now V in starts to change at 7 microseconds. So we're going to just put a dot there. And it takes 3 microseconds to get to its maximum value, which is plus 12. So 3 microseconds after 7 microseconds is 10 microseconds. And we're going to get it changing like this. Then when does V in change again? Well, it changes from minus 10 volts to 0, and it starts to change at 12 microseconds. So 12 microseconds is the next key time. And what we're going to get is our value changing over 3 microseconds back down to 0. So we know that between that 10 microseconds and 12 microseconds there's no change. And then we're going to get this changing, and 3 microseconds after 12 is 15 microseconds. So we know that our graph is basically going to go down to 15 microseconds. Now you always end up with this wedge-shaped type output graph. Okay, part C. Part C is all about the graph shape. And when you've got a graph such as this, there is certain key bits of information you should be able to glean quite quickly from it. Now the first of those is this going to be inverting or non-inverting? And this is quite important because the question actually asks, it says, following graph shows the input-output characteristics of a voltage amplifier. Design a voltage amplifier based on a single op-amp that has a characteristic curve. Draw a fully labelled circuit diagram to show your design, show clearly component values. Now, you obviously need to know whether it's inverting or non-inverting. And this graph shape means that it's non-inverting. And that's obviously going to have implications in terms of the circuit diagram. The next bit is what values does it saturate at? Well, this saturates at plus or minus 10 volts. And lastly, we need to know the gain. Now the gain for this is given by V out over V in. And what we're going to do is use that saturated value. Therefore, it's going to be 10 over, and it's the value at which it starts to saturate. So the V in value is 0.25. That gives us a gain of 40. Now that's quite important because for a non-inverting amplifier, gain is equal to 1 plus RF over Rin, or R1. And therefore, what this tells us is that what we have is a ratio for RF to R1 of, just get rid of that, of 39 to 1. In order to get our gain of 40, we need 39 divided by 1 plus 1, and that gives us 40. Okay, so now we should be able to draw the graph. All right, so draw the op-amp first. We know it's non-inverting, therefore V in will be attached to the non-inverting input. We also need a V out. It's always good to label V in and V out. Now, for this particular configuration, we need 2 resistors. So R1 will be attached to 0 volts. And we just need to make sure that we've got the terminal connection there. And then RF, our feedback resistor, is connected across the top. So we have RF and R1. Right, now we need to put in values. Now we know that RF is 39 times bigger than R1. The smallest value you should use is 10 kilo ohms. So we'll put 10 kilo ohms for R1. And RF has got to be 39 times bigger. And therefore, it's 39 kilo ohms. And therefore concludes question 4.